Let us do a more interesting example of a contour integral. This is the integral we wish to evaluate. It's a real integral as it looks. It's got cosine pi x divided by 1 plus x to the 4 dx. The integral is from 0 to infinity. A semicircle contour is what you will need if you have an integral that goes from 0 to infinity, because what you can do is make the integral go from negative infinity to infinity, go up a contour, and then take half the value. The complexification of this integral is given here. At the end, we'll take the real part, and the real part of this is just that. So the denominator is going to have some simple poles, but 1 plus z to the power 4 can be factored using the fourth roots of unity. So z to the power 4 plus 1 is 0 whenever z to the 4 is minus 1. Now, rather than guess, it's better to do this systematically. The principal value of the 0 is going to be e to the I pi, because e to the I pi is cosine pi plus I sine pi, and that's equal to minus 1. But also you will get the same answer if you add any multiple of 2 pi times k times I. So we can do that, and then take the fourth root of both sides. So that gives me e to the I pi by 4 plus ik pi by 2 for k equals 0, 1, 2, and 3. These are the fourth roots of unity. So the four roots we have can be written as a set, and these are the simple poles. E to the I pi by 4, e to the I 3 pi by 4, e to the I 5 pi by 4, and e to the I 7 pi by 4. It might be worth drawing or plotting the fourth roots of unity in the Argand diagram, or the complex plane. So that's the imaginary axis, that's the real axis. The fourth roots of unity are going to lie essentially in a square like that. That's your z1, z2, z3, and z4. And also a unit circle. We'll go through all of them. You can actually write this out in its proper form using Euler's formula. I'll do this one. That's cosine of pi by 4, which is 1 over root 2, plus I times sine of pi by 4, which is 1 over root 2. Once you have that located, the remaining ones can be written out simply based on the quadrant location. So z2 is negative x component, positive y component, negative x, negative y, positive x component, and negative y component, simply thinking of them complex numbers as vectors. So now all we have to do is apply the residue theorem and things will go nicely. So let f of z be equal to e to the I pi z. Observe that when I deduce the pole structure, I also have to make it a check if the numerator vanishes anywhere where the denominator vanishes. It does not, because then the pole structure will be more complicated. So that's 1 plus z to the power 4. So the residues can be computed by the simple method of all residue computations if there are simple poles. So residue at the zjth pole is just going to be the limit as z goes to zj of z minus zj f of z. So I'll perhaps show you the details of doing one of them, and then the details of doing another one will be left as an exercise for you to do. Now, why did I just say 2 rather than 4? We don't need 4 of them. So the choice of contour will basically decide how many residues we need to calculate. The contour we're going to consider is going to be the following. we're going to go from minus rho to rho being the magnitude of the complex number, and then go to infinity in such a way that you put a feed tube around these poles. So Z1 and Z2, because we're being in the upper half plane, sometimes called UHP, we don't have to worry about Z3 and Z4. Well, if you want, you can take a lower contour. It's up to you, but upper contour is enough. Now, the other thing that we have to also check, which I'll indicate at the end, is how this contribution vanishes as the contour goes to infinity. It makes sense, because if Z goes to infinity, the denominator gets really big. But we have to be a little more careful because these are complex numbers. So I'll outline that procedure towards the end. But right now, our main concern is to find these residues, because the residue theorem of Koshi has to be used. So we have to find the residue of this at this value and at that value. Let me just show you how to find the residue at value Z1, and the Z2 can be extrapolated from that. So it's the limit as Z goes to Z1, Z minus Z1 times f of Z. Well, f of Z has got all this. So I'll write this as e to the I pi Z divided by Z minus Z1, because we have factored the denominator. So I can write this as a product of the factors of the fourth roots of unity. Observe that Z minus Z1 cancels out, and that's the only trouble spot. So this is going to give us a finite value. And I won't go through the details. You should try this on your own. You will get the answer, e to the I pi over root 2, e to the pi over root 2 over 2 root 2 I times 1 plus I. It is a little bit of work to get to this answer, but it's just straightforward algebra. Similarly, the residue at Z2, the only thing that changes is that you'll have a minus sign here, here, and here. So this gives me e to the minus I pi by root 2, e to the pi over root 2 divided by 2 root 2 I times 1 minus I. Once you have these two, by the residue theorem, the value of the integral I, which I've indicated here, so by Cauchy's residue theorem, I is just 2 pi I times the sum of the residue in the interior of the contour C. That's the contour C. And so 2 pi I times all this, so the one factor of I will go away, and then you can simplify this thing. You'll end up getting pi e to the minus pi over root 2 cosine pi over 4 minus pi over root 2. It's a good exercise for you to try this. You have to use Euler's formula and then the formula of cosine of a plus b to finally simplify it to this form, where it should be done. Now, you may think that we have actually finished the problem, but this is just a start of it. The full integral is f of z dz counterclockwise, Well, that can be broken up into two integrals. That's integral minus rho to rho of e to the I pi x dx, because along the x-axis the y-coordinate is 0. So the exponential function e to the I pi z just becomes e to the I pi x. And then 1 plus x to the 4. Now this is really what you want, because the real part of this is our initial integral. And then you're going to also have this integral on the upper half plane along the contour. So I'll write c comma UHP e to the I pi z over 1 plus z to the power 4 dz. What happens to this one? You have to argue that it goes to 0. So let me run through that argument next. This type of argument will always be there in a problem like this. You have to argue away this term. So that's what we want to do. The argument goes as follows. The numerator can be written as, we can estimate the magnitude of the numerator. It's e to the I pi z. Well, that can be written as, z can be written as x plus iy. And if I multiply I times y with I get negative pi y. So this gives me e to the negative pi y. Well, that's a real number. You don't have to do anything with it. Times the magnitude of e to the I pi x. Well, no matter what that x value is, this is always going to be equal to 1. So the numerator is just e to the minus pi y. And this is always less than or equal to 1. I should have put the absolute value sign. Because y is always bigger than 0 in the upper half plane. Now what we're going to do is, we're going to have to evaluate the contour. So evaluate this term. So what I'll do is I'll parameterize the contour. The parameterization is z equals rho e to the I theta. Because you already add the value of rho, if you multiply by e to the I theta, you'll simply sweep the extent of the contour. Then dz is going to be I times rho e to the I theta d theta. Now we're going to use a inequality called the Koshi-Schwarz inequality, which I'll write here. How does that work? You estimate this integral e to the I pi z over 1 plus z to the 4 dz as being less than or equal to, by this particular calculation, the integral of dz over 1 plus z to the 4. That's what the Koshi-Schwarz gives us. The absolute value of the integral is less than or equal to the integral of the absolute value. That's called the Koshi-Schwarz inequality. Now, I'm going to put the parameterization that I have earmarked here for our, the inequality sign is still there, but this, from this step to this step, is an equality. 0 to pi, the magnitude of rho I, well, I rho e to the I theta d theta divided by 1 plus rho to the 4, because I have to fourth power that, e to the 4I theta all right, and then this thing is further going to be less than or equal to, now notice that the absolute value of I is just 1, the absolute value of e to the I theta is just 1, so I just have rho there. That's not where the inequality sign comes. The inequality sign comes when I choose to take the largest possible value The largest possible value in the denominator comes when e to the 4 pi I theta is equal to minus 1. So this is less than or equal to the integral from 0 to pi, the absolute value of rho, over 1 minus rho to the power 4. So that's a very interesting calculation, because now this whole thing is completely independent of theta. By using this clever argument that I'm taking the largest possible value of the denominator, I've gotten rid of the theta dependence altogether here. So this is just equal to 2 pi times the absolute value of rho over 1 minus rho to the power 4. And that's going to go to 0 as rho goes to infinity. Because the denominator, oh, by the way, I should put the absolute value, because rho is bigger than 1 as you go out to infinity. So that the denominator certainly dominates, and the contribution goes to 0. So this is how you show that this term is 0. Now once you have that, I am left with just the first term, and we can take the real part of the answer and get our integral. So let's finish up the problem. So therefore, the integral, which is equal to all of that, so pi e to the minus pi over 2 root 2 cosine pi over 4 minus pi over root 2, is equal to the integral from, I'm taking the limit now, minus infinity to infinity, e to the I pi x dx over 1 plus x to the 4. And now we'll take the real part of both sides, and also note that the integrand is an even function when I do that. So the value of this integral, the original integral, which is integral 0 to infinity cosine pi x dx over 1 plus x to the power 4, is just going to be half of this, pi over 2 e to the minus pi over root 2 cosine pi over 4 minus pi over root 2. And that is an answer that you possibly could not have dreamt in your wildest nightmares. You have to get it through complex integration.